Hi, my name is Jackson Mudio and I'm a sophomore studying mathematics. A fun fact about me is that I'm on the club swim team here at Chapel Hill. I will help students develop better learning and study strategies by promoting growth mindset and by reinforcing the belief that students should have in themselves.
An experiment is performed in which 10 milliliters of a 0.5 molarity solution of C6H5COOH is titrated to the equivalence point using 0.5 molarity sodium hydroxide. What is the pH before any of the solution, before any sodium hydroxide is added? And so to answer this question, we need to think about what do we have in solution at this point? We have acid and we have water. And so we need to immediately think Rice table. And so let's write a reaction. I'm going to represent this acid as just with a general HA that reacts with water. And we're going to use a double arrow because we're dealing with a weak acid with a very small K value. And this is going to form its conjugate base and hydronium. And so initially we have 0.5 molarity of our acid. We don't consider water because it's a liquid. It's not in our K expression that we're going to write in a second. We have no starting concentration of base or hydronium. And then we consider our change. We're going to lose some amount of our acid and form some amount of conjugate base and hydronium. And so at equilibrium, we will have 0.5 minus X, and then for our base and hydronium, we will have X and X. And so now we can use our K expression to help solve for our change, for our X. And so our K expression is significant because it's an expression that relates the concentrations of our products with the concentration of our reactants at equilibrium. And so let's write that expression. So we have a Ka of 6.3 times 10 to the negative 5 equals X squared, our concentration of our products, over 0.5 minus X. And before we proceed, we're going to make an assumption. We're going to assume that this change in X is very small, so small that it really doesn't affect our denominator that much. And so what we're going to do is we're going to omit this minus X. And this is going to make our calculation much simpler, much nicer. And so when we solve this, we get X equals 5.6 times 10 to the negative 3. And so what we've done is we've used the 5% rule. But now that we've done our calculation, we need to verify that that assumption was a valid assumption to make. And so how we do that is we take our change in concentration, 5.6 times 10 to the negative 3 molarity, and divide it by our initial concentration, and then multiply it by 100. And then we find that this value is much less than 5%. And so we have verified that our assumption that we've made is valid. And so now, this X value is the concentration of hydronium at equilibrium. And so we can just go ahead and calculate pH, knowing that P is just negative log of our concentration of hydronium at equilibrium, which is 5.6 times 10 to the negative 3. We find that our pH equals 2.25. This makes sense, right? Because all we have is acid and water. And so at this point, we should expect a pH less than 7.